Okay, hello everyone in a new video. So we have reached part 2 of chapter 4, which is the chapter of resistors and the second unit of electricity. Then we have reached section number 10, which is given by the grouping of resistors. And this section is known as also to be the equivalent resistance. Then let me start by some definitions or some notions, and let me say that the equivalent resistor of a grouping is the resistor that has the same resistance to that of the grouping. And notice that till this moment I didn't mention anything about the grouping. The grouping may be series or in parallel. So let me also say that another definition or notion of equivalent resistance is the following that. Let me say another way around. Is that the equivalent resistor is the resistor that can replace a grouping of resistors such that when we apply the same voltage or when the applied voltage is the same, when we apply the same voltage, then the same current will be traversing it. So now, in order to explain the following two notions, we need to refer to examples or to the type of groupings, and the first one is given by the series grouping. So let me say that section 10.1 is given by the series grouping. And by series, here we are referring to the electric components that are resistors, which means that they have only one terminal in common. Then let's consider a resistor R1. In series with another resistor R2. So these two resistors are said to be in series because they have one terminal in common. Let me name the terminals. So let's consider that this is the point A, this is the point B, and this is the point C. Now here we are saying that the equivalent resistor of a grouping is the resistor that has the same resistance to that of the grouping. So we need to replace these two resistors by a single resistor. So we need to replace them. So this is equivalent to a single resistor given by R equivalent, okay, having two terminals. Now notice that this point B disappeared, so we are left with the points A and C. So simply this equivalent resistor so EQ stands for equivalent, will replace the resistors R1 and R2. So basically, what's the relation between R equivalent and R1 and R2? Simply R equivalent is equal to R1 plus R2. So the equivalent resistor is a resistor that can replace resistors, a grouping of resistors. Here we are considering the series grouping, so notice that R1 and R2 are in series because they have one terminal in common, which is the point B. In this case, the R equivalent is given by R1 plus R2, so the point B will disappear and we are left with the points A and C. So this is the first definition. What about the second definition? Another way around, the equivalent resistor is a resistor that can replace a grouping of resistors. So indeed, here in this case, R equivalent replaced R1 and R2, but here we are mentioning that such that when we apply the same voltage, then the same current will be traversing it. Suppose here we connect it to a battery, so we have an applied voltage. So in this case, this is a closed circuit being traversed by the current I. Okay, so suppose that this is 12 volts, then in this case, suppose that I is equal to 0.5 amperes. So now because this grouping is being replaced by one resistor, if we connect it to the same battery which is given 12 volts, so 12 volts, then in this case the electric current I traversing this closed circuit is given by also 0.5 amperes because simply this equivalent resistor is equivalent to R1 and R2. Okay, so here let me give the following example. Suppose that the value of R1, let's say for example 2 ohms, and the value of R2 is equal to 3 ohms, and we are interested in determining R equivalent. So we simply say that R equivalent is equal to R1 plus R2, which is equal to 2 plus 3, so this is equal to 5. Since this is expressed in ohms and in ohms, which is the SI, then R equivalent will be expressed in ohms. Okay, so this is basically straightforward. Now as for the parallel grouping, because we know that we distinguish between two types of grouping, the parallel and the series. We have discussed the series. Now as for the parallel, then for this reason, let me consider two resistors that are in parallel. So suppose that this is the resistor R1 and this is the resistor R2. So these are the terminals of R1 and these are the terminals of R2. In order for them to be in parallel, both terminals must be connected to each other like this. And let's suppose that this is the point A and this is the point B. Now the equivalent resistor by definition is the resistor that can replace these two resistors, the grouping of these two resistors that are in parallel. So this is R equivalent. Having two terminals. So here no point will disappear, so this is the point A corresponding to the first terminal and this is the point B corresponding for the second terminal. So here if you connect this grouping to a DC voltage source, it will be traversed by current I, say for example of value 1 ampere. Then in this case, if you connect this R equivalent to the same battery, having the same applied voltage, then it will be traversed by the same current I, which is given by 1 ampere, say, for example, okay? But now we need to state the relation between R equivalent R1 and R2, and this relation is given by, so the formula that I have placed here in the box is we need to memorize. Now the other so this is what is for series, the other one is for parallel, which is given by R equivalent is the product of R1 multiplied by R2 divided by R1 plus R2 but the one that we will use more frequently is given by, or more often, is that 1 over R equivalent is equal to 1 over R1 plus 1 over R2. Okay, so we can either use this or this, and here let me state the following example. So suppose that R1, say for example, is given by say 4 ohms, and R2 is given by let's say for example 10 ohms. Then in this case we are interested in determining R equivalent. R equivalent, according to this formula, is given by R1 multiplied by R2 divided by R1 plus R2. So the value of R1 is given by 4, the value of R2 is given by 10, divided by the value of R1 is given by 4 plus 10. So this is 40 divided by 14. Since everything is expressed in the SI, so the value of R equivalent will be in the SI, which is ohms. Okay, and notice that this is a reducible fraction and it can be given by, so we can divide, so let me do it. So 40 divided by 14, then this is equal to 20 divided by 7 ohms. Okay, and in the decimal form it's given by 2.86 approximately ohms. Then another way to calculate R equivalent is using this formula. Now I will state the advantages and disadvantages of each one. Now in this case, 1 over R equivalent, so here I'm calculating it using another method, is equal to 1 over R1 plus 1 over R2. Then the value of R1 is given by 4, and the value of R2 is given by 10. Now notice that here we are adding two fractions, so we need to consider the common denominator, or we can simply plug this expression on the calculator and it's given by 7 over 20. Notice that in this case we didn't calculate R equivalent, we have calculated 1 over R equivalent. Then the value of 1 over R equivalent is given by 7 over 20. Notice that we are interested in determining R equivalent. In this case, if we cross multiply, then R equivalent will be given by 20 divided by 7. Since previously everything is expressed in the SI, then the value of R equivalent will be in the SI, which is ohms. So we should not forget this step, because this definition starts with 1 over R equivalent and not R equivalent. Okay, so it seems that this one is easier, because here it directly gives us the result. But what is important in this equation is that in case we have 3 resistors, we cannot use this formula. In case of 3 resistors, we will use this formula. Okay, so let me state the following. And this is an important note. In case of more than 2 resistors in parallel, say for example 3 resistors, then in this case the equivalent resistance is given by the formula. and we cannot use R equivalent is equal to R1 multiplied by R2 divided by R1 plus R2. Okay, we cannot use it. So we have the choice to use either this formula or this formula in case of two resistors that are in parallel. Whenever we have more than two resistors in parallel, 3, 4, and if we have 4 resistors, then we simply add 1 over 4, 5 resistors plus 1 over R5, etc. Okay, in case of more than 2 resistors, we must use this formula. Okay, so from the early beginning we will admit this formula and not the first one. Okay, now in case more than 2 resistors in series, suppose here we add another resistor R3 to be in series, then R equivalent is simply the sum which is given by R1 plus R2 plus R3. Okay, and now let's solve the following exercise as a direct application on what I have explained. Exercise 7. They are telling me that find the equivalent resistor of the following groupings. In each case we have the value of R1, R2 and R3. Let's start by the part A. So notice that in the part A we have 2 resistors that are in series because they have one terminal in common, which is the point B. So always from the early beginning we need to mention the type of a grouping. So here we need to say that R1 and R2 are in series, and this statement is very important, so they usually give it half a mark. So in this case, now after we have identified the type of grouping, we know that whenever 2 resistors are in series, their equivalent resistance is given by the sum. So we always in physics we start by writing the formula, which is R equivalent is equal to R1 plus R2. Notice that this formula is not dictated by any law, so no need to mention any law. The value of R1 is given by 20, the value of R2 is given by 15. Plugging this on the calculator, then R equivalent is given by 35. Since R1 and R2 are expressed in ohms, so the value of R equivalent will be expressed in ohms. So R equivalent is equal to 35 ohms. So this is it for part A. And now as for part B, so notice that in part B we have 3 resistors that are in series. The point E is a common terminal for R1 and R2. The point F is a common terminal for points R2 and R3. And here, before we move to part B, let me also mention the following note. So here I have mentioned note number 1. Let me mention note number 2. After determining an equivalent resistance, an equivalent resistor, it is convenient to represent this resistor instead of the grouping itself. So whenever we calculate an equivalent resistor, we need to sketch the equivalent resistor. Okay, so now because we have calculated an equivalent resistor, this equivalent resistor will replace R1 and R2, so it's given by this. Then the point B will disappear. We have the point A, the terminal C. This is R equivalent, and the value of R equivalent is given by 35 ohms. Now in part B they are telling me, so we have 3 resistors. Let me say, okay, the value of R1 is given by 20, this is 15, and this is 40. So before we calculate the equivalent resistor, we need to mention whether they are in series or in parallel. So here it's very clear that they are in series. Then let's say R1, R2, and R3 are in series. And in this case, the equivalent resistor is simply given by the sum. So R equivalent is equal to R1 plus R2 plus R3. So this is statement, this one here, it is important, and they usually give it half a mark. And first we need to always start by the formula. Here no need to mention any law because this is law independent. Now the value of R1 is given by 20. The value of R2 is given by 15. The value of R3 is given by 40. Now plugging this on the calculator, then the value of R equivalent is given by 75 ohms. So R equivalent is given by 75 ohms. Then the equivalent resistor that replaces this grouping or this configuration is given by R equivalent. And notice that here an important note is that whenever we calculate an equivalent resistor, we need to represent it or we need to sketch it. So in this case, the points A and F will disappear and we are left with the terminals D and G. So this is R equivalent. So it's not important whether we write R equivalent on the resistor itself or below or above. So this is the point D. This is the point G. And the value of R equivalent is given by 75 ohms. So this is it for part B. Now as for part C, we are asked also to calculate the equivalent resistance of this grouping. First, we need to notice what's the type of this grouping. Notice that they have two terminals in common. They are given by A and B. So let's mention that R1 and R2 are in parallel. So usually they give it half a mark. Then in this case, you will say that 1 over R equivalent is equal to 1 over R1 plus 1 over R2. Here, because the grouping is made up of two resistors, we are free also to choose the following formula, which is given by R equivalent is equal to R1 multiplied by R2 divided by R1 plus R2. But we will stick to this one. So now in this case, the value of R1 is given by 20. And the value of R2 is given by 15. Now here we are adding two fractions. We need to consider the common denominator, then we need to simplify the fraction, or directly we can plug this on the calculator. Then the fraction is given by, first let me calculate it. Then it's given by 7 over 60. Notice that in this case we didn't calculate R equivalent, however we determined 1 over R equivalent. So 1 over R equivalent is equal to 7 divided by 60. Notice that we are interested in determining R equivalent, so if we cross multiply, then R equivalent is given by 60 divided by 7. Since previously everything is expressed in SI, which is ohms, then the value of R equivalent will be expressed in ohms. Always, all quantities in physics must have unit. And as we have said that whenever we calculate an equivalent resistor, we need to represent this resistor in the grouping instead of the grouping or in the electric circuit. So here all the terminals will be present, nothing will disappear. So R equivalent of value R equivalent is equal to 60 divided by 7 ohms replaces R1 and R2 across the terminals A and B. Now finally, for the final part, which is the part D, so as usual, before we calculate the equivalent resistor, we need to specify the type of grouping. Notice that R1, R2 and R3 are in parallel. So this statement, they usually give it half a mark. Then in this case, the equivalent resistance is given by 1 over R equivalent, which is equal to 1 over R1 plus 1 over R2 plus 1 over R3. The value of R1 is given by 20, so 1 divided by 20 plus 1 divided by 15. And the value of R3 is given by 40. Now here we are adding three fractions. We need to consider the common denominator and simplify it, or we can simply plug this expression on the calculator and it's given by 17 over 120. Notice that in this case we didn't determine R equivalent, we determined 1 over R equivalent, which is given by 17 over 120. Because we are interested in determining R equivalent, so if you cross multiply, the value of R equivalent is the reciprocal, which is given by 120 divided by 17. Since everything is expressed in the SI, so the value of R equivalent will be in the SI, which is ohms. And always whenever we calculate an equivalent resistor, we need to represent it on the electric circuit or instead of the grouping. So this is R equivalent. No points here will disappear. So R equivalent is given by 120 divided by 17 ohms, and these are the terminals C and D. So this is it for this exercise. Now let's move to section number 14. So now till this moment, what are the different methods that allows us to determine the resistor? So the direct method is using Ohm's law, another one using the slope formula. So the third one is using an ammeter. What is an ammeter? An instrument. So notice that this word can be split into two words, ohm and meter. Ohm stands for resistance and meter is an instrument. So it is an instrument that measures the resistor. So we will skip method number 5. As for method number 4, which is extremely important, and this is from the indications, and let me write the following note. Given a lamp L having the indications, say for example 6 volts and 0.5 amperes, we know that these indications cannot be used whatsoever unless the lamp is functioning normally or if we are calculating its resistance. So I repeat, given the following indication 6 volts 0.5 amperes, we know what does these indications mean. Rated voltage and rated current under which the lamp function normally. We are not allowed to use them whatsoever unless the lamp is functioning normally, or we can use them if we are calculating its resistance. So here by applying Ohm's law, U is equal to Ri, and constructing the triangle of this formula, U will be at the top, R and I at the bottom. Putting our hand over R, so R will be given by U divided by I. Even though they didn't mention that the lamp L is not functioning normally, we can use that U is equal to 6 and the current I is given by 0.5 because R is constant and is independent of the functioning of the lamp. So I repeat, we can use these indications in only two cases: if the lamp L is functioning normally or if we are calculating its resistance, as we shall see in this exercise. Now exercise number 9, they are telling me given a lamp L acting as an ohmic conductor. So what is meant by ohmic conductor? Then we can apply Ohm's law. With the following indications 12 volt and 0.5 amperes. Now in number 1, they are telling me what does each of the above indication means. Let's start by 12 volts. We know it's the rated voltage of which electric component of the lamp L? Under which it functions normally. Now what about the 0.5 amperes? Always quantities can be referred to the unit by referring to the unit. Notice that amperes is the unit of current, so this is the rated current of which electric component of the lamp L under normal functioning, or under which it functions normally. Now as for number 2, they are telling me to calculate the resistance RL of L. Since here in the question they specify that this is considered as an ohmic conductor, then because they have specified that it is considered as an ohmic conductor, then we can apply Ohm's law. But notice that these indications are related to the normal functioning. Here in this case, because we are calculating the resistance and they didn't mention that the lamp is functioning normally, we can use them. Why? Because we are calculating resistance. So let's say apply Ohm's law, and we are applying Ohm's law to L. Ohm's law in general, so we always start by writing the general form, which is given by U is equal to Ri, knowing that we are interested in determining the value of R. So constructing the triangle of this formula, here because we have multiply, then U will be at the top, R and I at the bottom. We are interested in determining the value of R. Putting our hand over R, then R, which is denoted by RL, is given by U divided by I. So here U will take the value 12 and I will take the value 0.5, although the lamp L is not functioning normally, but here we are allowed to use them simply because we are calculating its resistance. Then 12 divided by 0.5, plugging this fraction on the calculator, then RL is given by 24. Since U and I are expressed in the SI, so the value of RL will be in the SI, which is ohms. Then in this case, RL is given by 24 ohms. So now exercise number 10, they are telling me given two resistors R1 and R2 such that R1 is equal to 10 ohms and R2 is equal to X ohm. So X here is an unknown. For this reason is being represented, the value of R2 is being represented by X. Find X in the following cases. So they are telling me that R1 and R2 are connected in series such that R equivalent 15 ohms. So notice that because they are in series, so let's say that R1 and R2 are in series. Notice that we are interested in determining the value of X having R equivalent and R1. So in this case, because they are in series, so this statement they usually give it half a mark. Then R equivalent is given by R1 plus R2. Notice that we are interested in determining the value of X, or in other words R2. So what's the type of this equation? This is a linear equation and one unknown. The value of R equivalent in the SI is given by 15. The value of R1 is 10 and the value of R2 is represented by X. So how do you solve this equation? We place X on one side and all the other numbers on the other side. Then X in this case is given by 15 minus 10, which is equal to 5. And always in physics, all quantities must have unit. It happens sometimes that in some cases that quantities doesn't carry any unit or don't carry any unit. And this is one of them, simply because here the unit is placed outside of X, okay? So this is important that here X doesn't carry any unit. Suppose by mistake we have placed that X is equal to 5 ohms. So suppose that we have done this by mistake. So in this case, if X is equal to 5 ohms, then the value of R2 is given by X ohms, which is equal to 5 ohms multiplied by ohms, which is equal to 5 multiplied by ohms to the power 2, which is wrong. Now if you consider the case where X is equal to 5, in this case R2 is equal to X ohms, which is equal to 5 ohms, and this is correct. And here there is a reason why they have labeled this quantity by X, because usually we do this in math, and we know that in math quantities doesn't carry any unit, don't carry any unit. So whenever quantities or values are represented by unknowns like X, Y or Z, this must give us a hint that this value must not carry any unit. So in this case, the value of R2, which is x ohm, is equal to 5 ohms. So the value of R2 is equal to 5 ohms. And always, whenever we calculate equivalent resistor, we need to represent this resistor. So this is R equivalent, having a value of 15 ohms, that replaces the two resistors R1 and R2 such that R1 is 10 ohms and R2 is 5 ohms. Now as for part 2, now they are in parallel. Then here, idea number 2, let me state that R1 and R2 are in parallel. Notice that the aim is not to calculate the R equivalent, but rather to calculate the unknown value x, and this is related to R equivalent. In order to find the value of x, simply we need to fit x in an equation. Usually this statement they give it half a mark. Because they are in parallel, then 1 over R equivalent is given by 1 over R1 plus 1 over R2. Okay. Now we are interested in determining the value of R2 because x appears explicitly in R2. So the value of R equivalent is given by 3.75. The value of R1 is given by 10. And the value of R2 is represented by x. Now how do you solve this equation? So first of all, this is not a linear equation. This equation consists of fractions. How do you solve this equation? We try to put x on one side and all the other numbers on the other side. So we move this number to the left, we move this fraction to the left, it will gain a minus sign. Then 1 over 3.75 minus 1 over 10 is equal to 1 over x. Then we need to subtract these two fractions, so we need to consider the common denominator, then we need to simplify it. Or simply we can plug this expression on the calculator. Then this is given by 1 over 6. So in this case 1 over 6 is equal to 1 over x. Notice that we are interested in determining the value of x. So in this case x is equal to 6. Now this quantity is labeled by x to give us a hint that it carries no unit. So all quantities in physics must have unit, and it happens sometimes that quantities doesn't have unit, and this is one of them. So in this case R2 in this case is given by x ohms, which is equal to 6 ohms. So R2 is equal to 6 ohms. And whenever we calculate an equivalent resistor, it's very convenient to represent it instead of the grouping. So in this case R equivalent is equal to 6 ohms across these two terminals. That replaces R1 and R2. And now let me solve extra exercise number 1. So this exercise is not found in the notes in the PDF, so then I prefer that you write it down on your copybooks. Now they are telling me consider a lamp L carrying the inscriptions 9 volts 0.3 amperes and the dry cell of constant voltage UPN. Then as I have mentioned previously, then the trick in solving such type of exercises is to label the voltage and the current on the electric circuit itself. But notice that in this case, since these values represents the inscriptions, then we are not allowed to use them or label them on the circuit until they mention that the lamp or the electric component is functioning normally. L acts as a resistor. So they are telling me that the lamp L acts as a resistor, then which means it's a ohmic conductor, which means that we can apply Ohm's law to L of resistance RL. Okay, so here we have that the lamp L has the following indications that are given by 9 volts 0.3 amperes. In addition to that, it has a resistance RL. Now they are telling me in order to function normally, so they mention function normally. So now the applied voltage across the lamp is equal to the rated voltage. And the electric current traversing the terminals of the lamp is given by 0.3 amperes. So why I have done so? Because they mentioned that the lamp is functioning normally. is connected in series with the resistor R of resistance R document 2. They mentioned document 2, so now we can use it. In number 1, they are telling me what does each of the inscriptions carried by L represent. Now 9 volt, these are the inscriptions. So notice that 9 carries the unit volt, which represents the voltage. Then it is the rated voltage of which electric component of the lamp L, under which it functions normally. Now as for 0.3 amperes, this quantity carries the unit amperes, which means it is electric current. Then it is the rated current of the lamp L, under which it functions normally. Now as for number 2, they are telling me determine RL. So knowing that the voltage across the lamp is 9 volts and the traverse current is 0.3 amperes, then we can apply Ohm's law. Here we have 3 electric components, the battery and the lamp and the R, but because we are determining RL, then we need to apply Ohm's law to L. Always in physics we need to mention the law that we are using, so they usually give it half a mark. And we start by writing the general form, which is given by U is equal to R multiplied by I. Notice that we are interested in determining the value of R. So constructing the triangle of this formula, here because we have multiplied, then U will be at the top, R and I at the bottom. Putting our hand over R because we are interested in determining RL, then it's given by U divided by I. So U is denoted by UAB and I is I. So the value of U is given by 9, the value of I is given by 0.3, and this is equal. Plugging this fraction on the calculator, then this is given by 30. Since U and I are expressed in the SI, so the value of R will be in the SI, which is ohms. Then RL is equal to 30 ohms. Now in number 3, they are telling me show that the current passing through R is I is equal to 0.3 amperes. So notice that here, because the lamp L is functioning normally, so the traverse current is 0.3 amperes, and because the resistor and the lamp are in series, then they are traversed by the same current, which is 0.3 amperes. So let me say first, since the lamp L is functioning normally, then the traverse current is equal to the rated current of the lamp L. So we mentioned the lamp L here. Then in this case, I is equal to 0.3 amperes. Now we know that the current traversing the lamp is given by 0.3 amperes, but they are asking me about the current that is passing through R. So we need to say that L and R are in series. Then according to law of uniqueness of currents, they have the same current, which is given by I is equal to 0.3 amperes. So now we know that the current traversing the resistor R is given by I is equal to 0.3 amperes. Now in part 4, they are telling me using the law of addition of voltages, this is important, calculate the voltage UBC across R knowing that UPN is equal to 12 volts. So the trick is to label this voltage here. Then as a title we start by apply law of addition of voltages. So always on the left we write the voltage of the battery, which is given by UPN, and on the other side of this equation we write the voltages across different electric components starting from P and ending with N. Then from P we'll go to the point A. From A we will go to the point B. From B we will go to the point C. And from C back to N. Notice that I have started with P on both sides, ended with N with both sides, and each letter we have inserted what? Twice, okay? And we are interested in determining the value of UBC across the resistor R. The value of UPN is equal to 12 is justified. As for UPA across P and A we have a connecting wire, and we didn't justify this previously, so between brackets UPA is equal to 0, and the reason is given by connecting wire. Now as for UAB is equal to 9 volts because the lamp is functioning normally. UBC is kept as a variable because we are interested in determining UBC. Plus UCN, across C and N we have a connecting wire, and we didn't justify this previously. So in this case we have that 12 is equal to 9 plus UBC. So what's the type of this equation? This is a linear equation and one unknown. The unknown is UBC. So how do you solve this equation? We put UBC on one side and all the other numbers on the other side. Then UBC is equal to 12 minus 9, which is equal to 3. Since both 12 and 9 are expressed in the SI, so the value of UBC will be expressed in the SI, which is volts. Then UBC is equal to 3 volts. And the trick in solving such type of exercises is to write the applied voltage on the electric circuit itself. So here we have 3 volts. Now finally in part 5 they are telling me to deduce R. What does R represent? So R represents the resistance R of the resistor R. So and by deduce it means that we need to use the previous part. In the previous part we have determined the applied voltage and already we have the traverse current. Then R can be determined using Ohm's law. Then apply Ohm's law. We are applying Ohm's law to which electric component? To the battery, to the lamp, or to the resistor? For sure to the resistor, so to R. And always in physics we need to mention the law that we are using, so this usually give it half a mark, as well as for this. Then U is equal to Ri, the general form, knowing that we are interested in determining the value of R. Constructing the triangle of this formula, here because we have multiply, then U will be at the top, R and I at the bottom. Putting our hand over R, then R, which is denoted by R, is equal to U divided by I. Now in this case this voltage is given by UBC, so we use the same notation, which is equal to 3 divided by 0.3. Plugging this fraction on the calculator, then the value of R is given by 10. Since both 3 and 0.3 are expressed in the SI, so the value of R will be in the SI, which is ohms. So R is equal to 10 ohms. And we are done with this exercise, and here let me mention the following. So usually each exercise in physics have a specific aim, and the aim is usually related to the last part of this exercise. So notice that here what we have, the problem is that we have a battery that have a voltage 12 volts, 12 volts, and a lamp having 9 volts as a rated voltage. We know that if you connect the lamp L directly to the battery, this will burn out the lamp, or it will may function strongly. Okay, so in order for the lamp L to function normally, we have one solution is to replace the battery by another battery having an applied voltage equal to the rated voltage. But in this case, this solution is commercially expensive, so batteries are usually expensive. However, in order for the lamp L to function normally, we can simply bring a resistor, and each resistor is characterized by its resistance. So we bring a resistor of resistance R is equal to 10 ohm, and we connect it in series with the battery, series with the lamp, then connect it back to the battery. This will make the lamp L functions normally, instead of going and replacing this battery by another one of 9 volts. Okay, so that's it for me in this exercise. In part 3 we'll complete exercises on this chapter.